Play any video of a black hole backward. Any video, a simulation, a visualization, anything. Play it in reverse and watch what happens. Matter does not fall in, it flies out. Light does not get trapped, it escapes. The singularity does not crush, it creates. The event horizon does not swallow, it vomits. Everything about the black hole, every property, every behavior, every terrifying feature runs perfectly in reverse. The accretion disk spins in the opposite direction, flinging matter outward instead of funneling it inward. Stars that were shredded by tidal forces reassemble. Photons that were trapped in the photon sphere spiral outward to freedom. The gravitational lensing that distorted the background star field smoothly undistorts. It looks wrong. It looks like a mistake in the editing, but the equations do not agree that it is wrong. That reversed object has a name. It is called a white hole. And the most unsettling thing about it is not that someone imagined it. It is that Albert Einstein's own equations demand it. I have spent more time thinking about white holes than any other topic in this series, not because the physics is the most complex. It is not, compared to the inside of a black hole or the first second after the Big Bang, but because the question it forces you to confront is not about astronomy, it is about time, about why time moves in one direction, about whether that direction is permanent, and about whether everything you think you know about cause and effect is just a local habit of a temporary universe. A white hole is the time reversal of a black hole. Where a black hole is a region of space that nothing can escape, a white hole is a region of space that nothing can enter. Matter and light can only come out. The boundary, still called an event horizon, works in the opposite direction. Instead of a one-way door inward, it is a one-way door outward, a cosmic exit with no entrance. Most people hear that and immediately ask, do they exist? That is the wrong first question. The right first question is, why does the most successful theory of gravity, a theory confirmed by GPS satellites, gravitational wave detectors, and photographs of black hole shadows, insist that they should? To answer that, I need to tell you about a man who solved the most important equation in physics while dying on the front lines of World War I. Karl Schwarzschild was a German physicist serving in the Imperial Army on the Russian front in 1915. He had access to Einstein's newly published field equations of general relativity, a set of equations so difficult that Einstein himself had not solved them for any realistic scenario. Schwarzschild solved them in a trench. He found the exact solution for the gravitational field outside a spherical mass, the simplest possible case, and mailed the result to Einstein. Einstein was reportedly amazed that an exact solution existed at all. Schwarzschild died 4 months later from a disease contracted on the front. He was 42. I want to pause on that for a moment because I think it matters. The first exact solution to the most important equation in modern physics was found by a dying man in a trench, not in a comfortable university office, not over years of careful study.
In a war zone, under fire, with months to live, Schwarzschild did not even know what his solution described. The term black hole would not exist for another 50 years. He was solving a mathematics problem. The universe was hiding a monster inside the answer. His solution, the Schwarzschild metric, described what we now call a black hole, though the term would not be coined until 1967 by John Wheeler. It predicted an event horizon, a singularity, and the complete collapse of matter beyond a critical radius. But for decades, most physicists believed the singularity was a mathematical artifact, a sign that the coordinates were wrong, not that space-time actually broke down. Arthur Eddington, one of the most respected physicists of the era, openly dismissed the idea that stars could collapse to a point. He called it absurd. Robert Oppenheimer and Hartland Snyder published a paper in 1939 showing that gravitational collapse was real, but World War II interrupted the work, and the physics community did not return to it seriously until the late 1950s. The solution also contained something else, something that would take physicists decades to fully understand. The solution had a second region. In 1960, the mathematicians Martin Kruskal and Karl Szekeres independently worked out the complete, maximally extended version of Schwarzschild's solution. The full picture was not one object, it was 4 regions of spacetime. Region 1, the exterior of the black hole, normal space, where we live. Region 2, the interior of the black hole, inside the event horizon, where everything falls toward the singularity. Region 3, a second copy of the exterior, another universe or another region of our universe. And Region 4, the interior of a white hole, a time-reversed region where a singularity in the past expels matter outward through an event horizon that nothing can cross inward. 4 regions, 2 horizons, 2 singularities, one in the future, one in the past. Connected by a bridge of space-time that pinches to 0 width faster than anything can cross it. This bridge is the Einstein-Rosen bridge, what science fiction calls a wormhole. I want to be clear about what this means. The complete, mathematically rigorous solution to Einstein's equations for the simplest possible gravitational object, a non-rotating, uncharged mass, requires the existence of a white hole. It is not an add-on, it is not a patch, it is the other half of the solution. Removing the white hole from the Schwarzschild solution is like removing the negative numbers from algebra. You can do it, but you have broken the mathematics. In 1964, the Russian physicist Igor Novikov was the first to take white holes seriously as astrophysical objects. He called them lagging cores and proposed that they might be delayed remnants of the Big Bang, regions where the expansion of the early universe got stuck and are now releasing their trapped energy. The idea was taken semi-seriously for about a decade, then it faded. Not because anyone disproved it, but because no one could figure out how a white hole would form, and no one could find one. Physics moved on. White holes became a footnote in textbook chapters about Penrose diagrams. I think that was a mistake, and I think the reason it was a mistake is becoming clear only now in the 2020s as quantum gravity starts to produce actual testable predictions for the first time. But before I get to that, I need to explain the real reason white holes are so disturbing. It is not that they are exotic, it is that they should not exist if time has a direction, and they force us to confront the possibility that the direction of time is not fundamental. It might be an accident. Here is the problem. Every fundamental law of physics, every single one with one tiny exception, works exactly the same forward and backward in time. Newton's laws, Maxwell's equations, Einstein's field equations, Schrödinger's equation, Dirac's equation. Take any of them, replace t with minus t, and the equation still works.
The laws do not care which direction time runs. An apple falling from a tree and an apple flying upward into a tree are both valid solutions to Newton's equations. One of them happens, the other does not, and the laws themselves cannot tell you why. The tiny exception is CP violation in the weak nuclear force, a subtle asymmetry observed in certain particle decays, first discovered in 1964. Kaon and B-meson decays show a slight preference for one direction of time over the other, but the asymmetry is absurdly small, far too small to explain the arrow of time we experience. It cannot explain why coffee cools, or why you age, or why the universe started in a low entropy state. The weak force knows the difference between past and future, but it barely cares. The arrow of time we live with comes from somewhere else entirely. This is the problem of the arrow of time. We experience time as having a clear direction. The past is fixed, the future is open. Coffee cools down, eggs break, people age, memory works backward but not forward. But none of this is built into the fundamental laws. The arrow of time comes from one place and one place only, the second law of thermodynamics. Entropy, the measure of disorder, always increases, or rather it overwhelmingly tends to increase because there are enormously more disordered states than ordered states. So a system randomly wandering through its possible configurations will almost always end up in a more disordered one. This is not a law in the same sense as gravity or electromagnetism. It is a statistical tendency, an extraordinarily reliable statistical tendency, so reliable that it functions as a law for all practical purposes. But it is not built into the equations. It is emergent. It comes from initial conditions, not from the dynamics. And this is where white holes become genuinely threatening to our understanding of reality. Because general relativity is time-symmetric, it allows black holes and white holes with equal mathematical validity. But the second law of thermodynamics is not time-symmetric. It picks a direction. It says entropy increases, not decreases. A black hole, which swallows matter and increases entropy, is thermodynamically natural. A white hole, which expels matter and would represent a massive decrease in entropy, is thermodynamically almost impossible. Almost, not completely. And that almost is where some of the most interesting physics of the 21st century lives. Stephen Hawking addressed this in 1976. His argument was pragmatic. Even if white holes could somehow form, they would be catastrophically unstable. Any matter or radiation in the external universe falling toward a white hole's event horizon would pile up on the boundary, and the accumulated energy would eventually cause the horizon to flip, transforming the white hole into a black hole. A white hole in a universe that contains anything at all would immediately self-destruct. Hawking concluded that white holes were mathematical artifacts, not physical objects. I believed this for years. It is a clean, satisfying argument. The universe is full of matter and radiation. White holes are allergic to matter and radiation. Therefore, no white holes. Case closed. Think of it this way. A white hole is like trying to hold a door open outward in a hurricane. The door wants to push things out. The hurricane wants to push things in. The hurricane wins instantly. The hurricane, in this case, is the entire content of the universe. Every photon, every neutrino, every particle of dust, all of which would crash into the white hole's event horizon and convert it into a black hole before you could blink. A white hole in our universe is thermodynamically suicidal. Except the case is not closed. and the reason it is not closed is a man named Carlo Rovelli. Rovelli is an Italian theoretical physicist and one of the founders of loop quantum gravity, one of two major approaches to unifying quantum mechanics with general relativity, the other being string theory. In 2014, Rovelli and his collaborator Hal Haggard published a paper that reopened the white hole question in a way that I think has not yet received the attention it deserves. Their argument goes like this. In classical general relativity, a black hole contains a singularity, a point of infinite density where the equations break down. But classical general relativity is almost certainly wrong at those scales.
Quantum effects must become important when the collapsing matter reaches the Planck density, roughly 10 to the 93 grams per cubic centimeter, the density at which quantum gravity dominates. At that density, the classical singularity is replaced by a quantum bounce. The matter does not collapse to infinity. It reaches maximum compression, then rebounds. This is not speculation in the way that wormholes or time machines are speculation. Quantum bounces are a robust prediction of loop quantum gravity, supported by the mathematics of the theory and by cosmological models where the same bounce mechanism replaces the Big Bang singularity with a big bounce from a previous contracting phase. If the black hole's interior bounces rather than collapsing to a singularity, then what comes out the other side is a white hole. The matter that fell in is expelled. The event horizon flips from inward to outward. The black hole becomes a white hole. And here is the critical detail. From the perspective of the infalling matter, from the reference frame of the stuff inside the black hole, the bounce happens quickly, Planck time quickly, roughly 10 to the minus 43 seconds. The matter hits maximum density and immediately rebounds. But from the outside, from our reference frame, the bounce takes an extraordinarily long time. Time dilation near the event horizon stretches the internal Planck time bounce into an external duration that could exceed the current age of the universe. Let me make sure you understand what this implies. Every black hole that has ever formed is, according to this model, in the process of bouncing into a white hole right now. But the bounce is so time dilated that none of them have finished yet. We are surrounded by black holes that are mid-transformation. They are all becoming white holes. We just have to wait. How long? Rovelli estimates the bounce timescales as the mass of the black hole squared in Planck units. For a stellar mass black hole of about 10 solar masses, the external bounce time is roughly 10 to the 34 years. For comparison, the universe is currently about 10 to the 10 years old. We would need to wait a trillion times the current age of the universe for the first stellar mass black holes to finish their bounce and appear as white holes. I find this simultaneously beautiful and infuriating. Beautiful because the mathematics is elegant and the physics is consistent. Infuriating because it means we cannot test it by simply looking for white holes in the current universe. They have not had time to appear. Or have they? In 2018, Rovelli and Francesca Vidotto proposed that primordial black holes, tiny black holes that may have formed in the very early universe from density fluctuations, would have much shorter bounce times due to their small masses. A primordial black hole with a mass of roughly 10 to the minus 5 grams would have a bounce time comparable to the current age of the universe. These bouncing primordial black holes would be converting into white holes right now. And as they do, they would release a burst of energy. What kind of energy? Rovelli and Vidotto calculated that the signal would be in the radio frequency range.
A brief, intense pulse of radio waves from a compact source with no obvious progenitor. A fast radio burst. Fast radio bursts, FRBs, were first detected in 2007 and have been one of the great mysteries of observational astrophysics ever since.
They are extremely brief, milliseconds long, extremely energetic, and come from cosmological distances. Most are now thought to originate from magnetars, highly magnetized neutron stars. But not all FRBs fit the magnetar model cleanly. Some are one-off events with no repetition and no identified host. These orphan FRBs remain unexplained. I want to be careful here. I am not saying FRBs are white holes. The magnetar model explains most of them convincingly. But the fact that a quantum gravity prediction made independently of FRB observations naturally produces a signal that looks like an unexplained subclass of FRBs is the kind of coincidence that physicists pay attention to. If even one FRB were confirmed to come from a white hole, it would be the first direct evidence for quantum gravity. That is not a small thing. That would arguably be the most important observation in the history of physics. Let me be specific about what to look for. A white hole burst from a primordial black hole bounce would have several distinguishing features. First, it would not repeat, unlike magnetar FRBs which often recur. The bounce happens once. Second, it would have no identifiable host object, no neutron star, no galaxy center, no obvious source. Third, the energy spectrum would be different from magnetar bursts because the emission mechanism is fundamentally different. It is not magnetic reconnection, it is the release of quantum gravitational energy stored for billions of years. Fourth, the signal might contain a specific spectral signature related to the Planck scale, a fingerprint of quantum gravity itself. No FRB detected so far has been conclusively identified as a white hole signal.
But the catalogue of FRBs is growing rapidly. TRIME alone has detected thousands, and the tools to analyze their properties are improving. We are not there yet, but we are closer than most people realize. There is another potential signature. When a black hole bounces into a white hole, the transition involves a change in the geometry of the event horizon. This geometric change would produce gravitational waves, but with a different signature than the chirps from black hole mergers that LIGO detects. The white hole bounce signal would be a single pulse, not a chirp. Current gravitational wave detectors are not sensitive enough to detect these pulses from primordial black hole bounces, but next-generation detectors like LISA or the Einstein telescope might be. Now, let me talk about the possibility that keeps me up at night. The Big Bang looks exactly like a white hole. I am not saying this as a metaphor, I am saying it as a description. The Big Bang is a singularity in the past from which all matter and energy emerged. Nothing fell in, everything came out. The event, whatever it was, produced an expanding spacetime that nothing can enter from the outside. These are the defining properties of a white hole. The Big Bang, described in the language of general relativity, is indistinguishable from a white hole event. Lee Smolin, a theoretical physicist at the Perimeter Institute, took this idea to its logical extreme in the 1990s with his theory of cosmological natural selection. Smolin proposed that every black hole that forms in our universe creates a new white hole, a new Big Bang on the other side. That new Big Bang produces a new universe with slightly different physical constants.
That new universe produces its own stars, its own black holes, and its own baby universes through its own white holes. The process repeats, with natural selection favoring universes whose physical constants maximize black hole production, because those universes produce the most offspring. This is a genuinely testable prediction, by the way. Smolin argued that our universe's constants should be near optimally tuned for black hole production. Change any fundamental constant, the strength of gravity, the mass of the electron, the cosmological constant, and you should produce fewer black holes, not more. Several physicists have checked this, and the results are surprisingly consistent with Smolin's prediction, though the analysis is complex and contested. If Smolin is right, then white holes are not rare or exotic, they are the most common events in the multiverse. Every black hole is a white hole from the other side. Every universe is the output of a white hole. We live inside one. I have thought about this a lot. The implication is staggering. Our universe contains roughly 40 billion stellar mass black holes. If each one eventually bounces into a white hole that seeds a new universe, then our universe alone is the parent of 40 billion child universes. And each of those children will produce their own black holes and their own children. The structure is not a tree, it is an exponential explosion of realities, each one slightly different from its parent, each one branching into its own descendants. And it goes backward too. Our universe was seeded by a white hole, which was the bounce of a black hole in a parent universe. That parent universe was itself seeded by a white hole bounce from a grandparent universe. The chain goes back indefinitely.
There was no first universe in this model. The chain is eternal. This is speculative. I want to be transparent about that. Smolin's cosmological natural selection is a beautiful idea with testable predictions, but it has not been confirmed. Some physicists find it compelling, others find it unfalsifiable in practice, even if falsifiable in principle. I sit somewhere in the middle. I find it too elegant to dismiss and too unproven to believe. It is the kind of idea that haunts you without convincing you. The Einstein-Rosen bridge, the wormhole connecting a black hole to its white hole counterpart, deserves more attention than most videos give it. In the original Kruskal and Szekeres geometry, the bridge exists but is not traversable. It pinches shut faster than light can cross it. You cannot enter a black hole, travel through the bridge, and emerge from the white hole. The geometry forbids it. This is a result of classical general relativity alone, without any quantum effects. But several physicists have proposed modifications. Juan Maldacena and Leonard Susskind suggested in 2013 that entangled particles are connected by microscopic wormholes, the ER equals EPR conjecture, where ER stands for Einstein-Rosen bridge and EPR stands for the Einstein-Podolsky-Rosen entanglement paradox. If this is correct, then every pair of entangled particles is connected by a tiny, non-traversable wormhole. The universe would be threaded with trillions of invisible bridges, none of them usable for transport, all of them connecting what we thought were separate regions of spacetime. Rovelli approaches the same idea from a different angle. In loop quantum gravity, the Big Bang singularity is replaced by a big bounce, a quantum bounce from a previous contracting phase. This is mathematically identical to the black hole bounce that produces a white hole. The Big Bang was a white hole, not metaphorically, literally. The mathematics is the same.
I want to pause and say something that I do not think anyone says often enough in these kinds of videos. We do not know if any of this is true. Loop quantum gravity is a serious, mathematically rigorous approach to quantum gravity, but it is not the only one, and it has not been experimentally confirmed. String theory offers a different picture. The firewall hypothesis offers another. We are in a period of physics where multiple consistent theories make mutually exclusive predictions, and we lack the experimental tools to decide between them. Anyone who tells you they know what happens inside a black hole, including me, is telling you what their favorite theory says, not what the universe has confirmed. But I will tell you what I personally find most compelling and why. I find the Ravelli bouncing black hole model compelling because it solves multiple problems simultaneously. It eliminates the singularity, the infinite density that everyone agrees is not physical. It connects black holes and white holes through a concrete quantum mechanism. It naturally produces the Big Bang as a special case. It makes a testable prediction, primordial white hole bounces producing signals we might detect, and it explains why we do not see white holes yet without invoking any new physics beyond quantum gravity. The model also preserves information. The information that falls into a black hole is not lost. It emerges when the black hole bounces into a white hole. This solves the information paradox that Hawking identified in 1974 and that has tormented theoretical physics for 50 years. The information is not destroyed, it is delayed. Delayed by an obscenely long time, but not forever. Now, let me bring this back to the question of the arrow of time, because that is the thread I want to follow to the end. If general relativity allows both black holes and white holes with equal mathematical status, and if quantum gravity provides a mechanism that converts one into the other, then the asymmetry between them is not fundamental, it is temporal. Black holes are common because we live in a young universe with lots of collapsing matter and low initial entropy. White holes are rare because the bounces have not had time to complete. But in the far future, 10 to the 34 years from now and beyond, white holes could become as common as black holes are today. This means the arrow of time, the direction that distinguishes black hole from white hole, the direction that makes coffee cool instead of heat up, the direction that makes you remember yesterday but not tomorrow, is not a fundamental feature of the laws of physics. It is a feature of where we are in cosmic history. We live in the black hole era. The white hole era has not started yet. There is something about this that changes the way I think about time. We treat the arrow of time as if it is obvious and universal. Of course, the past is behind us. Of course, the future is ahead. Of course, eggs break and do not unbreak. But the equations do not say, of course. The equations say both directions are equally valid. We happen to live in a universe, or a phase of a universe, where entropy is increasing, and that gives us a past and a future and a sense of direction. But that sense of direction is not carved into reality. It is a feature of our epoch. A civilization living in the white hole era, if such a thing could exist, would experience time in the opposite direction. Their future would be our past. Their entropy would decrease from our perspective. They would remember what we call the future and predict what we call the past. Communication between us would be meaningless because our respective arrows of time point in opposite directions. We could not agree on which way cause and effect run. I do not know if this is true. Nobody does.
but I find it the most honest answer to the question this video started with. Do white holes exist? The mathematics says yes. The thermodynamics says not yet. The quantum gravity says they are forming right now, invisibly, inside every black hole in the universe. And if they do eventually emerge, they will force us to confront the possibility that the direction of time is not a law, it is a circumstance. Let me try to make this concrete, because I think the implications are wilder than they sound. You remember the past. You do not remember the future. That feels fundamental. It feels like the most basic fact about consciousness, about experience, about being alive. But it is not fundamental. It is entropic. Your brain forms memories by creating ordered structures, neural connections, protein configurations, electrochemical patterns. Creating order in one place requires creating more disorder somewhere else. That is the second law. Memory formation increases total entropy. The direction of memory is the direction of entropy increase. If entropy were decreasing, memory would work in the other direction. This means that a being living in the white hole era, if such a being could exist, would not experience the white hole as something bizarre. To them, it would look normal. Matter would emerge from a singularity and spread outward. That would be their Big Bang. Their arrow of time would point away from the white hole, just as ours points away from the Big Bang. They would form memories in the direction of increasing entropy within their phase of the universe. They would not think anything was backward. They would think we were the ones running in reverse. I find this the most disorienting idea in all of physics, more disorienting than black holes, more disorienting than quantum mechanics, more disorienting than the expansion of the universe, because it suggests that the experience of time, the feeling that this moment is happening now, that the past is gone and the future is coming, is not a feature of reality. It is a feature of thermodynamics. Change the thermodynamics and you change the experience. The now that you feel is not written into the fabric of space-time. It is written into the gradient of entropy, and entropy gradients are temporary. There is one more thing I want to say about white holes, and it is the thing I have been building toward. The reason we do not see white holes is the same reason we do not see eggs unbreaking, coffee unspilling, or smoke unrising from a cigarette. It is the same reason you are older today than yesterday. It is the same reason you cannot unsay something you have said. The second law of thermodynamics selects one direction and suppresses the other. Black holes are the cosmic version of an egg breaking, a natural entropy-increasing process. White holes are the cosmic version of an egg unbreaking, mathematically possible, but entropically forbidden in the current era. But Rovelli's model says the era changes. Given enough time, grotesque, incomprehensible amounts of time, the black holes bounce. The eggs unbreak, not metaphorically, physically. The singularity reverses. Matter comes back out. The entropy accounting balances over cosmic timescales that dwarf anything we can imagine. If this is true, then a white hole is not the opposite of a black hole. It is the future of a black hole, and possibly the past of a universe. And the reason you cannot find one is not that they do not exist, it is that you are too early. The universe has not finished making them yet. Next time, there are black holes wandering through our galaxy right now. They have no stars, they emit no light, they are invisible, and one of them might be closer than you think.